Okay guys, so this is our third lesson looking at a homeostasis mechanism in the body, and we're looking at osmoregulation today. So osmoregulation is talking about how water levels are controlled in the body, so making sure the amount of water carried around in our blood and just generally present in our bodies is at a suitable and safe level. I'm sure you're aware that water levels being too low is a dangerous thing, dehydration, but water levels can be too high as well, which can also be dangerous. So we want to make sure that our water levels are balanced in a steady state, and homeostasis and negative feedback allow that to happen. So I've put here that the kidneys are very important in regulating water levels, especially what we call the nephrons. So the nephrons are tiny functional units in the kidneys, and that's where water is able to be reabsorbed or nutrients are taken out of water. You don't technically need to know in detail how the nephron works, but I thought I'd just give you a bit of an overview of that anyway. So, we've got here. So yeah, water and small solutes can enter the nephron from the blood. Larger things are filtered out, but water, salts, glucose, they can enter. And then as they move along, important nutrients are reabsorbed into the body. Okay? And as they go down this loop that they call the loops of Henle, water is able to exit. Okay, so it can exit here, and that can get reabsorbed where it's needed to. So salts exit the loop of Henle on this bit going up, and they do that by a mixture of active and passive transports. So passive transports, things like diffusion, when they just move out from high to low concentration, and then sometimes active transport is required when they need to move against the concentration gradient. Okay, up at the top, there's further reabsorption of water and mostly of the nutrients that may be dissolved in it. Then finally, last bits of water leave, and further salts can leave as well, going down here, and then the urine is basically what's left after this stage. And depending on how much water is reabsorbed, that affects how concentrated the urine is. So if lots of water is being reabsorbed throughout these steps, especially at the end, then the urine, so the water's being reabsorbed into the body, the urine will be very, very concentrated. There won't be much water in it. If not much water is being reabsorbed back into the body, the urine will not be very concentrated. Okay? So you can have a study of that in your own time if you want to pause the video and have a read through it, or look at another diagram online of how the nephron works. But like I say, you don't really need to know how they work in any great detail for Unit 1. Just be aware that the nephrons are where the water is reabsorbed. Okay? So a bit of key terminology when we start studying how the negative feedback works for osmoregulation. When we're referring to high osmotic pressure, that means there's a low water concentration in the blood. So the blood doesn't have as much water as it should have. So that's called high osmotic pressure. It's called that because that means water is likely to move from the kidneys back into the blood through reabsorption. High water concentration in the blood means low osmotic pressure, basically meaning that water is not likely to move by osmosis from the kidneys into the blood. Okay, so in a little while I'm going to talk about osmotic pressure, and that's just what I'm referring to. When I say high osmotic pressure, I mean there's a low amount of water in the blood, and when there's a low osmotic pressure, there's a high concentration of water in the blood. And then for how the body picks up on these, remember when we're talking about stimuluses and responses, we always have to talk about how the changes in the environment are received. But we've got osmoreceptors in the hypothalamus in our brain. You may remember the hypothalamus is also involved in temperature control, and that the osmoreceptors in the hypothalamus pick up on the water levels, whether they're too high or too low, and they coordinate the response we're going to look at in a second. Before we look at that, just wanted to share an example of an animal that's well adapted for their environment because of their kidneys. So we're going to look at the behavioural, structural and physiological adaptations like we did a few lessons ago for the kangaroo rat, and one of these adaptations is linked to their kidneys and how they help them survive. So there's my 5 out of 10 drawing of a kangaroo rat, I reckon, if we're being generous. But they're a small rodent that lives in the North American plains, especially, well, more the deserts of North America. So they live in very, very warm environments with not a huge amount of water. Okay. So like I say, one of their major structural adaptations is they've got really, really long loops of Henle in their kidneys. Just to remind you, the loops of Henle are the bits of the nephrons that go down and water can get reabsorbed into the blood from them. So by having an extra long loop of Henle, that allows these animals that live in the desert to absorb much more water and keep more water in their body. They've also got a physiological adaptation linked to the structural one. They produce highly concentrated urine, so lots and lots of salts and urea, not a whole lot of water, so they keep more water in their body. And as a behavioural adaptation, I've just put in that they seek shade in extreme heat. And those things linked together all make the kangaroo rat really well adapted to its environment in dry desert plains in North America. Okay. So the last thing that I want to talk about is just the how the negative feedback feedback loop works for returning osmotic pressure to normal, returning it to a healthy range when it changes. So always starts with a change from normal. So maybe the osmotic pressure rises falls below the normal level when there's too much water, or maybe the osmotic pressure rises above normal when there's too little water. Either way, the hypothalamus, which is in your brain, detects that change. And if the osmotic pressure has fallen, what it does is it secretes less ADH. I can't remember if I mentioned ADH, but ADH is a hormone that's just important for controlling water levels. It's called antidiuretic hormone. So basically, if the water levels in the blood are too high, they won't secrete a lot of ADH. And part of that means the body won't feel thirsty, and also less water will be reabsorbed in the kidneys. Therefore, the osmotic pressure rises and it returns to the normal levels. Whereas if the osmotic pressure rises above what it should be, so there's too little water, again, the hypothalamus detects it, but this time more ADH, more antidiuretic hormone is secreted, and that will help the person to feel thirsty and want to drink. And then also that will result in more water being reabsorbed from the kidneys into the blood. The osmotic pressure rises and it rises up to a normal level at the end of that. Okay? So that's another negative feedback loop. The body detects change, what it should be at a healthy level, and it returns it to normal. So whether it's the osmotic pressure being too high or too low, the body will respond and return it to its normal level. Okay, so that is everything for covering that. Thank you.